All right, so guys, before we get too deep into what we're doing today, I want to draw our attention back to the calendar. Guys, we've got some things that are sort of in process right now, and guys, one of my best efforts to help you be successful is to try to help you be organized. So guys, rallying around the calendar right now, obviously today is November 4th, and guys, it's been a long time. We're actually going to go into lab and do a lab. It's been a while since we've got our hands dirty, so to speak, and we're going to do that today. There's a little bit of background information that you need to understand. We'll go over that in a minute, and then we'll get you over to lab. Then guys, coming back on Monday, we're going to get into a couple day period where we're going to start getting closer and closer and closer to that model of the atom. And I'll explain the journey a little bit more in a minute. But guys, understand that Monday, Wednesday, and Friday are all going to be lecture days. They're interesting. They involve homework. But guys, again, remember, we're all headed in a direction which is over here to the east wall of my room, which is this new and better understanding of what atoms are all about. We'll talk more in a minute. But guys, remember along the way, looking at the things in red, if you qualified for remediation, guys, that starts on Monday or Tuesday, one or the other. Remember, guys, there's stuff that you need to do in advance in order to qualify. All of that is on the front page of our website. And guys, it's critical that you follow along. If you don't follow the process, we won't let you participate in remediation. So that's either going to be Monday or Tuesday. And then, guys, the essentials test will then be on Thursday. But guys, you'll notice there's some more red on the calendar. The other thing that you need to keep in front of you is that your final papers are due on Friday. Now guys, please, if you need support on this, please come and talk with me. If you would like somebody to edit your paper, go down to the writing fellows who are in Mr. Ellingford's room every day during Flex. You don't have to be an Ellingford student to do that, and they will happily help you rewrite your papers. But guys, those are finally due Friday morning. You'll turn those in. I will then submit them to the English department graders, and it sounds like we may be getting them back a little bit before Thanksgiving. Guys, please make sure that you're looking at the instructions sheet when you write up this paper. It will be a cover page and then 2 to 3 typewritten pages. So guys, this is how the rest of the next couple weeks lay out in terms of deadlines, in terms of what we're doing with material. And then guys, I think I mentioned that day there, Monday before Thanksgiving break, is an activity that you could easily do from home. So if you're leaving early for Thanksgiving break, Monday is not going to be a problem. So guys, questions about the calendar or any of this? You guys all good? Okay. So guys, do this with me then. Grab that blank sheet of paper that you've got in front of you, and at the top of that, you could title, it's kind of notes. It's really more stuff you need to know for the lab. Guys, this would be the intro to the Bohr Model. Then guys, on the lab sheet that I gave you, make sure you put your name on there. And you may also want to write across the top of it that it's due on Monday. Guys, you will not get an additional day to work on this lab. Most of you will get it done today in class. If that's the case, just turn it in. But guys, these are finally going to be due on Monday. So again, guys, name, period B1, due on Monday, written on your lab. And then, guys, on your note sheet, intro to the Bohr model. And, guys, when we're done, I would say put these notes in the lab section of your notebook and not the homework or not the class notes section, because everything that you're going to write down today, frankly, is just the answers to the conclusion questions on the lab. So you're going to want those associated with your lab and not with your class notes. All right, you guys all settled and ready to go? All right. So, guys, this is the idea. Last time in class, we watched these videos, and they were mind-boggling, and they were really fast, and there was all sorts of pictures and ideas jumping onto the screen. But guys, you may remember that last time in class as we were watching the videos, I mentioned to you, guys, don't expect to understand this. And I may have even said, guys, if you're frustrated right now because you're used to understanding things and now you don't, that's good. Because, guys, remember, we are on a journey. Please don't write this down. But, guys, this is the journey that we are on. We have done all of this in the previous unit. We talked about Dalton. We talked about the plum pudding model. We talked about Rutherford's nuclear model of the atom. So, guys, everything that we did in the previous unit was to get to here. Now what we're going to do is we are going to jump down to the bottom of the diagram and we're going to start talking about electrons. So guys, this is the way the journey is going to go. Right now, today, we are going to build up the Bohr model of the atom. Then guys, over the next coming days, we are actually going to move into Schrodinger's model of the atom. Guys, in order to do this, we need to remind ourselves. So the Bohr model of the atom, which we call the planetary model, was discovered by studying light. And guys, that's what you're going to do today in lab. You are actually going to take atoms and you're going to force them to release light. It's actually a really cool lab. It's exactly what Niels Bohr did. The only difference is that Bohr did it mathematically and we're going to do it qualitatively and just look at all the pretty colors. But we're doing the same thing. Then, guys, we are going to move into Schrodinger's model of the atom, and we're going to start talking about waves, and we're going to start talking about all these dots and all these interesting ideas and probabilities. But, guys, this is how this is going to go. Today, we are going to build up the Bohr model of the atom. But, guys, the only reason we're building up the Bohr model of the atom is because we're then going to rip it apart. So when you walk out of class today, you're going to be like, okay, I understand some stuff about the Bohr model of the atom. I know how Bohr came up with the Bohr model of the atom. You're going to be feeling really good about the Bohr model of the atom. Then, guys, when I see you on Monday, our only purpose on Monday is going to be to destroy the Bohr model of the atom. So when you walk out of here on Monday, it's going to feel really weird because you're going to be like, wait a minute. Okay, I know the Bohr model's wrong, but I don't know what is right. Guys, that's where you're going to be on Monday. Then when you come back on Wednesday, we're going to make this leap and we're going to start talking about what do atoms actually look like. Yeah. Are you sure? Are you? Oh, good. You're okay? All right. So, guys, this then is where you want to start jotting down ideas. So, guys, how do we know about the Bohr model of the atom? And, guys, the answer is this. The Bohr model of the atom was discovered by studying the light that is released when electrons fall from higher to lower orbits. Guys, that's how Bohr figured out, that's how Bohr figured out that electrons are not plum pudding. What Bohr did was he took atoms and he actually excited the electrons in the atoms, and when they fell back down, they released light. And by studying that light, he was able to figure out the structure of these atoms. So, guys, this is kind of the idea. So, if we've got a book, and if we drop this book, it releases energy in what form? Sound, absolutely. And we also know that if we drop the book from a higher level, that was kind of weird, it releases more sound. Well, guys, the same thing is true of electrons. When electrons fall, they also release energy, but they don't release the energy in the form of sound. They release the energy in the form of light. And that's what you're going to do today in lab. But before you do, there's some terms you need to know. So, guys, this idea of falling from higher to lower orbits, those higher and lower orbits have names. And these you need to know to write up the lab. So, guys, the higher orbits are called excited states, and the lower orbits are called ground states. So guys, let me show you how this works. Don't write down the drawing that I'm about to throw up on the board. What you do need to know is excited state and ground state, and we're going to use them in context. Can I go forward? You got excited state and ground state? Okay, so guys, it goes like this. So this is the Bohr model of the atom. The red dot in the middle is obviously the nucleus, and then we've got one electron moving around the nucleus. But we understand that thing is in motion. And so guys, this electron is just moving around the nucleus like a planet moving around the sun. Now guys, that electron right now is in its lowest energy state. So what energy state is that in? You just wrote it down. That is its ground state. So then guys, this is what Bohr did. Bohr pumped some energy into this electron. And when he did, the electron jumps up into a higher energy level, a bigger orbit, and now this electron is moving through a bigger space. Guys, what do we call that bigger space? Pluto. What do we call that bigger space? That's an excited state. So the little guy is the ground state, the big guy is the excited state. To get it to go from a ground to an excited state, you have to add energy. By the way, guys, our source of energy is going to be heat from a Bunsen burner. So now this electron is up here in its excited state, and it's zipping around through a bigger orbit. But guys, it can't stay there. It doesn't want to stay in that excited state. So what it does is it falls back down to its ground state. Now guys, when it falls back down, it releases the energy back out in the form of light. Now guys, this is the idea. If we add a little bit of energy to this electron, it will jump up into an excited state like that. And then it'll fall back down and it will release that energy in the form of light. Now, if we add more energy to the electron, it will jump into a bigger orbit, and when it falls back down, it will also release that energy in the form of light. But here's the trick. Short falls release different light than long falls. Guys, in the same way that if a book goes through a short fall, it releases a little energy, and if it goes through this, it releases more energy. Electrons are the same. They release more energy in the form of light when they go through longer falls. Here's the question. How is the light different? How is short fall light different than long fall light? Zach, do you know? That's exactly what it is. Guys, some people think it's brightness. That if it's high energy light, it's bright. And if it's low energy light, it's dim. And that's not the case. Guys, the difference is color. And that's what Bohr figured out. He figured out that he could determine how far the electrons fell based on their colors. And so, guys, this is where you want to start writing this stuff down again. So when this energy comes out, it comes out in the form of what we call photons. Photons are packets of light energy. Now guys, these photons have different amounts of energy. And it's all about color. So guys, if you don't know the colors of the rainbow, you've got to get this in your notes. So guys, how do we know how far an electron fell? And the answer is color. And it's all about Roy G. Biv. So guys, the colors of the rainbow are given by Roy G. Biv: red, orange, yellow, green, blue. You're going to want this for the lab write-up. Green, blue, indigo, and violet. So guys, now all we need to know is which end is which. Which color, red or violet, is high energy, loud light, if you will, and which end is the low energy, softer light. Red is actually lower energy. Yeah, so that's why ultraviolet light gives you sunburns. This is the high energy, violet and ultraviolet, and that's the lower energy end. So guys, the question then becomes this. What is the difference between high energy light and low energy light? And guys, you want to scratch this down in your notes. All you need to draw is a wave that's spread out, and then a wave that's more repeated. So guys, when we draw these waves, we think about the distance between their crests. And you'll notice that this is what we call long wavelength light. The waves are longer. This is short wavelength light. And guys, that's the difference between the colors. Now we just need to make the connections. And guys, this is the last of the stuff that you need to know in order to be able to go into lab. So it goes like this. If an electron goes through a short fall, notice it's coming up below the diagram. If an electron goes through a short fall, just like a book going through a short fall, it will release low energy photons, low energy light. Low energy light has longer wavelengths. So guys, that is this. Low energy light is stretched out. It has longer wavelengths. This is red light. But then guys, the opposite is also true. If an electron goes through a long fall, it will release higher energy photons. And these high energy photons have shorter wavelengths. And guys, this is the blue and the violet end of the spectrum. So guys, if you've got an electron that goes through a short fall, low energy light, long wavelength, it'll appear more red. Longer falls, like a book falling from a higher elevation, higher energy, shorter wavelength, and that light is more like blue or violet. You guys okay? Questions or things we need to talk about? So guys, what I'd like to do then is I'd like to show you kind of what this looks like. Go ahead, David.
So, on the lab,
Yeah? Yeah.
it shows like the elements that were in the wave.
Exactly.
Like, for example,
What letter is it?
BA.
BA, so barium?
Yeah.
Okay.
But that ones have like a higher like wavelengths, so like a lot higher.
I love the way that you're thinking. So if we look at barium, barium's all the way down on the energy, all the way down on the periodic table, right? So does that determine the amount of energy that it will release? And the answer is not directly. It's strange. So there really is not a connection between location on the periodic table and the colors they release. The connections actually are more related to the electron structures and specifically the shapes of their orbitals and their sizes, and we're going to get into that next week, and then we can tie it back. Actually, the really interesting connections are what we do in AP when we actually do the math of this, and we can actually collect the light from these elements like barium, and what you'll see is, I think barium may actually be red, but if you pass that red light through a prism, you actually see that red light is actually made up of a lot of other colors of light, and we can take that light, spread it out, measure the wavelength of each of those bands, and then go back and figure out the electron structure. And the math is actually really pretty easy. So if you're interested, come back for AP because we do that next year. It's really kind of fun. All right, so guys, let me make sure you're where you need to be. If an electron goes through a short fall, low energy light, long wavelength, what color will that be? Red. Then if an electron goes through a long fall, that will be higher energy light, shorter wavelength light, and that light will be more towards the blue end of the spectrum. So guys, this is then kind of what it looks like in sort of diagram form, if you will. So guys, here are the energy levels, the orbits. So you can think of it like this. It's as if the nucleus is down here, and these are the orbits represented by the rungs of a ladder. And we're going to see these electrons falling from higher to lower energy levels. Yeah?
So when we did a lecture,
Yeah? Yeah. Yes. Exactly, and that's exactly what's happening is, remember, what is the, I love that you picked up on that. So where do the colors of the Bunsen burner flame come from? And the answer is the heat from the Bunsen burner excites the atoms in the air. So when you see that yellow and then that blue flame, what you're actually seeing is the nitrogen and oxygen in the air getting excited and releasing energy. But think about this. What flame are we looking for in order to know that we have a hot flame? The center, but what color is it? It's light blue. And that's the idea, is that the bluer light is the higher energy light, and we know that because it excites the electrons more, and we see that by color. Yeah, that's exactly the connection. So, yeah, go ahead, Zach. Oh my gosh, absolutely. And we're not going to talk about this a lot in this class, but this is also the way we make microwaves. This is also the way we make X-rays. So anything that's radiation, everything from radio waves all the way up to gamma rays, can be about this stuff. It's actually, so let me give you an example. If you've ever had a dental X-ray and they stick that thing against your face and they zap you with X-rays, what they actually do is this. They take titanium atoms, and titanium has a bunch of electrons in it, and it's got a bunch of energy levels, and what they do is they pass a current through the titanium, and what it does is it actually takes one of these electrons and adds so much energy to it that it goes away. It ionizes the titanium. But then what happens is an electron in the 6th energy level from titanium falls all the way from 6 to 1. And when it goes through that long of a fall, the energy that it releases is even beyond violet. It's X-ray radiation, which is even higher at radiation. But that's the way they do it. They excite titanium, blast an electron out, another one falls down to fill its place, and that fall is so long that it releases X-rays. Yeah, isn't that cool? It's really interesting. So guys, let me show you then what this looks like. So this is what you're going to be doing in lab. What this video doesn't show you is the excitement of the electrons. You're going to do that with the Bunsen burner flame, but you are going to watch the electrons fall. How are you going to know how far they fell? The color of the light.
An electron, which is in a higher energy level than its ground state, is said to be in an excited state. When an electron moves from a higher state to a lower state, a photon is emitted whose energy is equal to the energy difference between the initial and final states. This principle is illustrated here for an atom through the mechanical analogy of a ball on a staircase.
So guys,
transitions which produce photons of visible light for the hydrogen atom are referred to as the Balmer series.
So the idea is this, that when these electrons fall, they release light. Long falls, like 6 down to 2, are going to create more violet-colored light. Shorter falls, like 3 down to 2, will create redder light. So the longer the fall, the more violet the light.
An electron, which is in a higher energy level than its ground state, is said to be
more like bluish,
an excited state.
When
an electron moves from a higher state
like yellow-green
to a lower state,
to
a photon is emitted.
Redder light. So again, guys, the longer the fall, the more violet the light, and then the shorter the fall, the redder the light. Does that make sense? Okay, so guys, with that then, what are we going to do in lab? So guys, grab the labs and let's talk about what we're going to do. So guys, first of all this, you don't need to wear goggles during the lab. All of the solutions that we're going to use are completely safe. Don't get them in your eyes because they'll burn your eyes like it's salt water. So be careful. You don't want to get them in your eyes, but we're not going to wear goggles. So guys, read along with me starting in the procedure, and let's talk about how this lab is going to work. So guys, the very first thing you're going to do in lab is, there we go. You're going to go grab one of these. Guys, this is what is called a micro well tray. And what you're going to do is you're going to take the micro well tray, you're going to fill all the wells with tap water, just shake it out, rinse it a couple times, get it clean. Then guys, moving along, follow along with me. Guys, moving along into step 2, it says this. Fill the micro well tray. In the micro well tray, fill each separate well with the following metal ion solutions. And guys, notice they're in alphabetical order. Barium, calcium, copper, potassium, lithium, sodium, and strontium. Now guys, what you're going to see when you get into lab is we've got 3 boxes. And in those boxes are solutions of each of those, but we only have 3 sets. So guys, what we're going to need to do is spread them out throughout the room and then cluster together and set these up as lab groups, but you're going to have to share because we only have 3 sets of these. Now guys, understand that when it says fill the wells, you only want to fill them about 2/3 of the way full, but what you're going to want to do is do these in order. So you're going to go like barium, calcium, copper, or whatever's next, but do them in order so that you know what is what. Then guys, step number 5, you're going to get 5 Q-tips. You're going to break them in half, and magically you now have 10 Q-tips. Then guys, step number 4, you are going to place a Q-tip in each one of the solutions. Just stick it in there and let it soak. And as it soaks, what it's going to do is it's going to soak up these metal ions that are dissolved in water. Then guys, once you've got these soaked, let them sit for about a minute. What you're going to do is you are then going to add energy to the ions, to these metal atoms that are in solution. You're going to add energy to these things and you're going to excite their electrons. Here's how to do this. So guys, it says, step number 4, soak the swabs. Then, place the swab in the burner and watch for a color change. Repeat this until you get a good clear color and then record the color down here being specific. So guys, here's the way this is going to go. So we've got our Bunsen burner, and it's got this 2-part flame. Guys, that is where you want to stick the bulb of the Q-tip. Now here's what you're going to experience. When you first stick the Q-tip into the flame, it's going to sputter and it's going to turn yellow. What you're seeing there is the water evaporating. But then guys, once the water is all gone, then these really interesting, vibrant colors are going to shine through. And you're going to see violets and blues and greens and oranges and yellows. And guys, that's what you're looking for. Just a second, David. So the way this is going to go is this. Dip it, stick it in the flame, splatter, and as the water evaporates, then color. Do it again. Dip it, stick it, color. Do it multiple times until you're sure of what the color is. But guys, be careful, because if you leave it in the flame too long, the Q-tip's going to catch on fire. So there's a balance between seeing the color and catching the Q-tip on fire. If it catches on fire, run it underwater, put it out, throw it in the trash, get a new Q-tip. Yeah. That is exactly how fireworks work. So what you're going to see is the same colors that you're going to see in the flame test are the things that they use to create colors in fireworks. Yeah, absolutely. All right, so guys, continuing to read on with me then. Guys, looking at number 5. Paige, you're now distracting me, and that's not fair. If you don't care about the lab, just chill, and you can do the makeup later. But now I'm more concerned about what you're doing than what I'm doing, and that's not fair to me. All right, so guys, number 5. The next thing you're going to do is you're going to go back and you're going to test all 7 of these solutions, figuring out the flame test colors. Now guys, let's be clear. What do the colors represent? How far the electrons are falling. You stick them in the flame, they get excited. They jump to an excited state. When they move out of the flame, they lose that energy, falling back to their ground state, and you're going to know how far they fell based upon their colors. Then guys, step 6. This is where this gets interesting. It says fill new wells with each of 3 unknown solutions. Guys, there are 3 additional bottles in each set, and they're unknowns. What you're going to do is you're going to figure out what these unknowns are. But I'll tell you this, the unknowns are each is one of the 7 solutions you tested. So how are you going to identify the unknowns? Flame test them and compare the colors. So guys, reading on it says, be careful to keep them separate. Test each of the unknowns with the same procedure as in step 3. Use the known solutions to determine the identity of the unknowns. Then guys, when you're done, clean up your lab station, including, you can just put everything down the drain, rinse your well plate, make sure the gas is off, and put the micro well tray back. So guys, looking on the back, you'll notice that there's a place where you'll identify the colors of the 3 unknowns. And then, guys, in that space, you're going to identify, based upon comparison, what are the metals in those 3 unknowns. Then, guys, you've got 4 conclusion questions to answer. You'll find that the answers are in your notes, and these are due on Monday. We good to go? Okay, so guys, again, we don't need goggles. We're going to leave the lights off in the lab because it's easier to see the colors. And let's get next door. Go get them.